So now that we've talked a little bit about the composition of the atmosphere, 78% nitrogen, 21% oxygen, and 1% other stuff, today we're actually going to talk about the layers of the atmosphere. And this is from our textbook, pages 10 through 15. That's your reading assignment. Make sure you do it. But let's jump in. So just a quick review from last time, and that's the fact that the atmosphere is held in place by gravity. As a result, just like we hang near the surface of the Earth, most of the atmosphere's molecules also hang near the surface of the Earth. In fact, as I said last time, 99% of the molecules in the atmosphere hang out near the lowest 30 kilometers of the Earth, and it's approximately 19, 20-ish miles. And most of them are even located even closer to the surface. Now, this has some major implications when it comes to what's called density and pressure. And that's what we're going to begin today's lecture by talking about. First, let's talk about air density. So, air density is mass per volume. You don't need to memorize any formulas or anything, but think about this. Suppose you have two water bottles. One of them is empty and one of them is filled with water. Which one's going to be the denser one? Well, assuming that they both have the same volume, the heavier one is going to be the denser one. And that would be the one filled with water, right? So air density is simply the amount of stuff, the amount of air molecules, or the amount of any molecules that occupy a given space. It's the mass per volume again. Near the surface of the Earth, there's a lot of air around us. In fact, in the room that you're sitting in right now, there are trillions and trillions and trillions of air molecules floating around you. However, the higher you go up in the atmosphere, the less dense the air becomes. Soon, instead of trillions and trillions and trillions, it's just trillions. Then it's just billions. Then it's just millions. Then it's just thousands. And so on. So as you go up in height, up into the atmosphere, the amount of air molecules that occupy that space becomes less and less and less. This is why it feels like it's harder to breathe the higher up you are. Because it is. Because there's fewer oxygen molecules. So it's harder for you to breathe because you don't have as much oxygen. And if you are somebody who's training for a fight, like Conor McGregor, for his big fight in a few weeks, well, that's something that you want to actually do. You want to go someplace where there's less oxygen because it causes your body to work harder, makes you better prepared. But anyway, let's not talk about that. Let's continue on. So air density, how many molecules occupy a given space? Now, very similar to air density is something called air pressure. Air pressure is the weight of the air above you. Believe it or not, all of the air surrounding you right now actually has a weight to it. It actually has a force that's pushing down on your body. And it's actually a pretty substantial force. Assuming you're at sea level, and I don't know where you're watching this from, but assuming you're at sea level, take your index finger and your thumb and make a little circle with them. That would roughly look like a square inch. On that square inch, there is 14.7 pounds of air weighing down on you, just in that square inch. So our bodies are actually acclimated to this, otherwise we'd all be feeling very weighed down. However, the higher up you go in the atmosphere, there's less air above you. And since there's less air above you, air pressure also decreases. And because most of the air is near the surface, it decreases rapidly as well. So, again, air density decreases with height. Near the surface of the Earth, you have plenty of air molecules around you. The higher up you go, the fewer and fewer there are. Let's talk a little bit more about air pressure. So as I just mentioned, air pressure is the weight of air above you. Now there's a few numbers I want you to remember. I hate using the word memorize, but these are probably a good thing to memorize. So before we get into them, just remember that as you go up in the atmosphere, the amount of atmosphere above you decreases. As a result, air pressure decreases. Now here at the surface, these are the numbers I want you to memorize, surface air pressure is approximately 1,013.25 millibars. A millibar is the metric unit for air pressure. It's the one that's most commonly used by meteorologists like myself, and so it's the one I want you guys to know. I want you to know what a millibar is. However, if we were to look at imperial units, it's 29.92 inches of mercury. We'll talk about where that unit came from later in the course. Or, as I mentioned earlier, 14.7 pounds per square inch. So on every square inch of your body, 14.7 pounds weighing down on you. As you go up in the atmosphere, again, there's less air above you. Therefore, air pressure continuously decreases with height. And it decreases exponentially. And what exponential decreasing actually means is if you go up just a small amount, just a few hundred feet, between the surface and those few hundred feet, air pressure declines rapidly. It declines rapidly. Then the higher up you go, it's still declining, but it doesn't decline as quickly. So very small change near the surface creates a big difference in pressure. Very small change in height, big difference in pressure. Higher up you go, that same change doesn't cause as big a decrease. Looks something like this. So if you're near the surface of the Earth, air pressure is approximately 1,000 millibars. Memorize that number though, 1013.25. If you go up even just a slight bit, just up, just a little bit, you lose substantial amounts of pressure. And the reason why is because most of the air molecules hanging out near the surface. And then the higher up you go, the less it decreases, but it still continuously decreases. We'll talk more about this in a few weeks. But let's actually get to the gist of what I wanted to talk about in this lecture. So, we all know that our Earth is split up into different layers. Crust, mantle, outer core, inner core. If you don't remember that, the surface of our Earth, the land on our Earth, is split up into different layers. But actually, very similarly, the atmosphere is also split up into different layers. And it actually is split up into these different layers based on how temperature changes in each layer. So, before we move on, let me just review and say that as you go up in the atmosphere, pressure always declines. It always decreases. But that's not true about temperature. Believe it or not, temperature doesn't always decrease with height. It doesn't always decrease with height. Let's talk about this. Here near the surface, we're in a layer called the troposphere. In the troposphere, which is approximately the first 7-8 miles, 0 to 11 kilometers of the atmosphere, as we go up in height, temperature does decrease. That's a reason why snow is on the mountains. If you have ever seen Mount Hamilton to our east in the wintertime, gets snowy there. Whereas we don't get snow down here in Silicon Valley because the air up there is much colder. However, as you go into the next layer, the stratosphere, temperature actually increases with height. Then in the mesosphere, temperature decreases with height again. Thermosphere, temperature increases with height again, and so on. So it's almost like a zigzag type motion. And we'll talk about that later. Now, so we have these 5 layers: the troposphere, the stratosphere, the mesosphere, and the thermosphere. The place where one layer ends and another begins is what we call a pause. For example, the top of the troposphere is what we call the tropopause. Top of the stratosphere is what we call the stratopause. Top of the mesosphere is what we call the mesopause. Top of the thermosphere is what we call the thermopause. So if we actually look at a temperature profile of our atmosphere, which is just a graph of temperature versus height, what you see is that here in the troposphere, temperature declines with height. When you go up into the stratosphere, temperature increases with height, then it levels off and then decreases again in the mesosphere, then it levels off and increases substantially with height in the thermosphere. Just a quick review: anything on the right represents increasing temperatures, anything on the left represents decreasing temperatures. The bottom of the graph is the surface of the Earth. The top of the graph is the top of the atmosphere. Well, actually, that's way higher than this. But again, as you go up, temperature decreases in the troposphere, increases in the stratosphere, decreases in the mesosphere, increases in the thermosphere. Know this, love this, get used to this. We'll be talking about this a little bit more throughout this course, especially these lower 2 layers, the troposphere and the stratosphere. Now, the troposphere is actually where we're going to spend most of our time at this quarter. The troposphere is actually the lowest layer of the atmosphere. And it's the one that we live in. Unless you've been on a really high altitude flight or unless you happen to be an astronaut, chances are you have never and will never leave the troposphere. In the troposphere, there's a lot of mixing that occurs, and that's where we get our weather from. As we go up in the troposphere, as I mentioned, temperature usually decreases with height. Now there is one key exception to this, and this is a word I want you guys to really know. Don't just memorize it, make sure you truly understand what it is, and it's what's called an inversion. In an inversion, there's a shallow layer, usually near the surface of the Earth, where temperature briefly increases with height. Increases with height. And this is actually very common near the surface of the Earth on a warm summer day. When you actually do one of our module activities, you'll actually see what's called an inversion. And inversions are very important because they actually act like a lid, trapping the air beneath them from escaping. And so when we get an inversion, a lot of the pollution that we emit can actually hang out near the surface. Let's go up into the next layer. The next layer is called the stratosphere. And by the time you're in the stratosphere, you're going to feel like you're in outer space. If you've ever seen one of those videos of Lego Man in space or beer can in space, if you haven't, I say look them up after this. Finish this first, but then look them up. But if you have never seen them, usually most of those videos involve getting up into the stratosphere. The stratosphere is the second layer in the atmosphere, so it's just above the troposphere. And it has one very important characteristic to it, and it's where our ozone layer is. So that makes the stratosphere very important, because that's where our ozone layer is. Now, as I mentioned in the previous lecture, our ozone layer blocks harmful UVB and UVC radiation from reaching the surface of the Earth. Now, the way it does this is it absorbs those things. And when it absorbs them, it warms up. So the ozone actually warms up, and that causes temperature to increase with height in the stratosphere. And that's how we know that we've transitioned from the troposphere to the stratosphere. When temperatures start to increase with height, we've now entered the stratosphere. Now, one other interesting thing about this is just like that inversion near the surface of the Earth can trap air near the surface of the Earth, this inversion, this layer where the temperature rises with height, also traps all of the air in the troposphere from escaping. That's why weather is primarily restricted to the troposphere, because all the mixing that's happening can't reach into the stratosphere. There are a few exceptions, but for the most part, we'll stick with that. Now, before I continue, let me show you something really cool. Here on the right, I have this image. This image was taken in 2013, the very first year I actually taught this class, and it was of a gentleman named Felix Baumgartner. And Felix Baumgartner is what's called a free faller. Basically what he does is he gets into a pod with a gigantic balloon that carries him up into the higher troposphere and even into the stratosphere. Well, in 2013, he was sponsored by the people at Red Bull to go all the way up into the stratosphere at an elevation over 100,000 feet. And he free fell from there. In doing so, he broke the speed of sound, and he also broke the world record for the highest free fall. So, and this was an image of him just before he fell. And as you can see the curvature of the Earth back here. And it looks like you're in space. Now, going above the stratosphere, we get into what's called the mesosphere. This is really the only time I'm going to talk about the mesosphere. The mesosphere is the third layer in the atmosphere. Now, in the mesosphere, temperature again decreases with height. So once we pass that ozone layer, we lose the warmth, temperature decreases with height again. An interesting thing about the mesosphere is it's actually the coldest layer in the atmosphere. Temperatures in the mesosphere at the top of it get as cold as negative 90 degrees Celsius or negative 130 degrees Fahrenheit. So it gets really cold up there. What you see over here on the right, this is a picture of what are called noctilucent clouds. These are clouds that are present in the mesosphere that can actually become illuminated in twilight and in the evening. There's a whole video on noctilucent clouds. I'm not going to bore you with it, but they're pretty fascinating. Something else interesting happens in the mesosphere. The mesosphere is also the layer of the atmosphere where the air becomes thick enough for meteors that are approaching the Earth to begin to burn up. As they enter the mesosphere, the air density becomes great enough to where they begin to feel friction and they burn up. So meteors begin to burn up in the mesosphere. Now, above the mesosphere is the thermosphere. And I'm mostly intrigued by the thermosphere. The thermosphere is the layer above the mesosphere, and in the thermosphere, temperature increases with height again, and it actually increases substantially. This makes the thermosphere the warmest layer in the atmosphere. But let me give you a little disclaimer, and it's in the lower right of your screen. While it's called the warmest layer of the atmosphere, we're going to learn in a few weeks that warmth and temperature have to do with molecules. And so when we talk about the thermosphere being the warmest layer in the atmosphere, we're talking about on a molecular level, meaning the temperature of those individual molecules is extremely hot. However, if you happen to be in the thermosphere, air molecules are so few and far between. Think about the room that you're in right now. As I said earlier in this lecture, there are trillions and trillions and trillions of air molecules around you. Well, if you get up into the thermosphere, and if you were to pump out the air in your room right now and pump in thermosphere, you would have potentially as little as one air molecule in your entire room. Would that feel pretty warm? Not really. As a result, even though the thermosphere is the warmest layer in the atmosphere, it's only so on a molecular level. We'd still be very cold if we lived in the thermosphere. Another interesting thing about the thermosphere, though, is unlike those balloons that we supposedly send into space but really send into the stratosphere, in the thermosphere, this is where most of Earth's satellites, where space shuttles before they were retired, and the International Space Station all actually orbit Earth via the thermosphere. That's right. The International Space Station doesn't leave our atmosphere. It's actually present in the thermosphere. And then above the thermosphere, we have something called the exosphere. That's the only time I'm going to talk about it this quarter. So I'm not that interested in it. But as I just mentioned, the International Space Station orbits the Earth from the thermosphere, as does most of our satellites. Now, the last thing I'll talk about before we wrap up this lecture is something called the ionosphere. The way this works is when you're in the upper atmosphere, when you're in approximately the mesosphere and the thermosphere, there are very few molecules. However, those molecules, when the sun hits them, they absorb substantial amounts of radiation and they get very excited. Think about what you do when you get excited. You kind of glow, don't you? Maybe not like literally, but you glow. Well, when air molecules get excited, they glow. And as a result, they actually give off lots of what are called electrons. And these electrons actually electrically charge the ionosphere. They actually charge the ionosphere. Now, the ionosphere, it has some implications. We're not really going to talk about them. The thing I do want you to know about the ionosphere is that it's thicker during the day, thinner at night. It's thicker during the day because that's when the sun is hitting all these molecules, heating them up and exciting them. At night, no sunlight, no excited molecules. One interesting implication of this has to do with AM radio waves. During the daytime, AM radio waves actually can't penetrate too far into the ionosphere. And as a result, AM radio stations don't have really good reception. However, at night, when the ionosphere is substantially thinner, AM radio waves can actually travel hundreds of miles, maybe even thousands in some cases. Now, before I wrap things up, let me talk really quickly about temperature in the atmosphere. We define and divide these different layers of the atmosphere, troposphere, stratosphere, mesosphere, and thermosphere, by temperature changes. Temperature decreases with height in the troposphere and mesosphere, and increases with height in the stratosphere and thermosphere. So you get sort of a zigzag motion. Decreasing in the troposphere, increasing in the stratosphere, decreasing in the mesosphere, and increasing in the thermosphere. And you can easily identify a pause, the end of one layer and the beginning of the other, by looking at where the temperature levels off and then where it changes direction. However, be careful. Remember, there are inversions very commonly near the surface of the Earth. Where does the troposphere end? Well, to actually look at how it ends, we need to look at something called a skew T. And this is basically an advanced version of something called a Skew Diagram, which you're going to actually get to work on in a little bit. But what actually happens is, as you rise in the troposphere, air temperature decreases with height. However, what actually happens is somewhere in the troposphere, temperature levels off, like right here, and then it begins to increase. This right here represents the end of the troposphere and the beginning of the stratosphere. So, just a quick review. Air pressure and air density both decrease with height in the atmosphere. So as you go higher in the atmosphere, much thinner, lower pressure, that's why your ears pop. And then the atmosphere is divided into different layers: troposphere, stratosphere, mesosphere, and thermosphere. All right, that's enough for today. Thank you for listening. Thank you for watching. And our next talk is going to be on weather versus climate. Until then, I'm Terrence Mullins. Have a great day.